Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on November 11th, 2025, about 8 days ago. It shows that a selective thinking strategy can boost reasoning accuracy by about 8 to 11% compared with always doing 2 iterations, while skipping the extra pass for 94% of tokens. The paper is titled, Think at Hard, Selective Latent Iterations to Improve Reasoning Language Models. And as we will see, the idea of letting models think deeper only on hard tokens has surprisingly big implications for efficient reasoning. Also, the author shared an official GitHub repo for TAH. You'll find the full Python implementation of the selective latent iteration model, along with training and evaluation pipelines, dataset labeling and pruning scripts, playground inference examples, and ready-made configs for QN-based models and distributed training, so you can reproduce their results. Figure 1 makes the core message concrete. Always thinking twice can backfire, while thinking more only on hard tokens really helps. The left toy dialogue shows how a second latent iteration can ruin an already good reasoning plan, yet a targeted extra pass on the tricky decision tokens corrects the logic. The right pie charts quantify this, showing that selective iteration greatly increases helpful fixes and sharply reduces harmful revisions. Figure 2 explains how the model actually thinks selectively, both across tokens and across hidden iterations. So while Figure 1 made the motivation vivid, this figure shows that duo-causal attention lets each token look not only to earlier positions but also to shallower thinking depths, so information flows across passes. The left panels contrast regular causal attention with this two-dimensional version. On the right, the architecture diagram shows the base model plus low-rank adapters feeding into a neural decider, which either keeps iterating or verbalizes the token. Table 1 gives the punchline in numbers. Selective thinking with TAH reliably beats all other methods across every math benchmark and both model sizes. The table summarizes accuracy for the standard single-pass model, always think, with 2 passes everywhere, soft think and routing, which swaps between 2 separate models based on a learned gate. TAH lifts the average score from about 31 to 35 for the smaller model, and from about 48 to 53 for the larger model. TAH Plus, which allows a tiny parameter increase, does even better, nudging the averages a bit higher on both sizes. Table 1 showed that selective thinking beats all the baselines. Figure 4 shows that this advantage stays stable across different continuation thresholds. The continuation threshold controls how confident the decider must be before triggering a second latent iteration, which effectively tunes what fraction of tokens think twice. Accuracy on the GSM-8K benchmark peaks at a threshold around 0.9. Even when many more tokens iterate twice, performance stays close to that peak and remains above the standard and always think baselines. Table 2 shows that the specific architectural choices really matter for selective thinking performance. Low-rank adaptation, which is a lightweight way to add task-specific weights, and residual connections together give the best average accuracy across math benchmarks. Dropping low-rank adaptation or residuals steadily hurts the scores, so both pieces help the model refine hard tokens. Switching from duo-causal attention to regular causal attention lowers accuracy even more, which confirms that attending across both token positions and iteration depths is crucial. Table 9 makes the efficiency story precise. Selective thinking keeps computation almost as cheap as the standard single-pass model, while always think roughly doubles the work. Across all datasets, always think uses about 2 iterations per token, so its floating point operations per token jump by around 3 to 4 times. In contrast, TAH and TAH Plus stay near 1.06 iterations, adding only a small compute bump for sizable accuracy gains. Alright, the big lesson is that letting models think deeper only on hard tokens cuts latent overthinking and boosts math reasoning by roughly 5 to 10%, while keeping compute almost at single-pass cost. More broadly, it shows dynamic per-token computation is a powerful alternative to just scaling size. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.